So anyway, we have the project due this Saturday. I'm going to be posting the next project today sometime. And we'll be talking about that tomorrow. Tomorrow I'm just going to have an open work day. Hello? Did you hear that? Tomorrow's going to be an open work day if you want to come and ask me questions, help you with your code, whatnot. Or if you want help getting started on the next project, you can do that too. I'm going to try and be consistent about that. Have Thursday be just a work day. For those of you who aren't here, I will be available through a Google Chat if you want to chat with me. Anyway, so there won't be a lecture tomorrow. And if no one shows up, then I won't show up either.
Still be available through Google Chat.
Anyway, so let's go ahead and get started. So I'm going to talk a little more about OpenMP, this ccNUMA thing and why it's important. And then I had a request to talk about MatPlotLib, so I'm going to talk about that too. Alrighty, so there are some useful OpenMP functions. Hey, Cole's here. All right, so all of these functions are defined in the, oh, bother. I want a pen. Give me a pen, okay. Okay, so all of these are defined in the omp.h header file, so you have to include that if you want to use them. On top of that, you'll also have to compile with the appropriate flag in order to get the linking correct. If you don't have the flag, it won't be able to find these functions. Okay? So, first off, if you want better control over the number of threads that you're going to be using, you need to use the omp_set dynamic 0 function. You have to call that. It takes either a 0 or 1. 1 is on, 0 is off. And basically what that does is if it's on, it gives OpenMP more control over the threads. If you turn it off, it gives you more control over the threads. That's kind of the simplest explanation I can think of. If you want to set the number of threads, you use this function, where n is the number of threads you want. However, this is an upper bound only. The implementation can do whatever the heck it wants. It just can't go greater than that. And that's why we turn the dynamic off. It kind of gives you a little more control. I tested it with the GNU compilers, and it seems to do exactly what I want. You know, it gives me the threads that I want. So that's how you're going to, specify how many threads you want, is using these right here. So this one's really useful. Get thread num. So if we have a parallel region, some sort of parallel region here, and we want to know which thread is running, we need a private variable, call it ID, and then we get thread num. Okay, and so each thread now has its own variable that says, oh, I am thread 0, I am thread 1. And you can use that in your computations in order to split up loops if you want to do that manually, or maybe output to a different file, and so on. This one does the exact opposite. It tells you how many threads there are total running at the time that function is called. Okay. And here's another important one. OpenMP get W time. This gets you the wall time in seconds. You don't have to deal with clocks per second or casting integers to doubles or anything like that. And it works on Linux, it works on Windows, it works everywhere. So, and if you want to time something, you say start, and it returns a double, just so everyone knows. Start, get W time. And then we do an end. I can't write. And then to get the total time, all you have to do is end minus start. This is so handy, it might even be worth using it in serial programs to time things. Because it really is confusing, because some functions on Linux do something completely different on Windows, and so you have to account for that, and it's a pain in the butt. But this is the easy way to do it, is using get W time. So that's how you're going to be timing your next project, is using these functions. All right, now we need to talk about what's known as the implicit barrier or implicit blocking behaviors. Almost every single OpenMP section or construct has an implicit block at the end of it. So a for loop, for example, if we have this pragma OpenMP for loop, and then we yada, yada, yada. Okay. And so each thread executes its part of the for loop, and when it gets to the end, it stops. And it waits for everyone else to finish and get there. Okay, so that is the default behavior for the OpenMP for loop. You can, however, change this. If you use this statement here, we say no wait. When a thread finishes its section of the loop and it gets to the end, it keeps going. If you specify don't stop, no wait. However, no wait and reduction are not compatible with each other. Why is that?
Because reduction requires information from other processes.
Right. This will throw an error. You cannot specify no wait if you're doing a reduction. It has to stop and wait for everyone to finish so it can add all the results together. All right, so the single directive here says anything within this block, I only want one processor to run it. And it is blocking by default. So everyone else jumps to the end of that block and waits for that one processor to do its thing. All right, there's another one called master. Oh, I should note you can specify no wait on that. And what this does is only the master thread executes the section of code that you put in the braces. The master thread is the zero thread. He's the guy that starts running the program and then forks everybody. Yes?
What's the benefit of using the master versus just any random thread?
Consistency.
Default, isn't it?
If you need consistency, you should use master, because all the variables, the private variables that are available to master will always be the same. Whereas if you're using the single directive, it's random. It's whoever gets there first.
So single doesn't default to the master.
No. Generally, it's whoever gets there first, even though that's not stated in the standard. It's just one. It doesn't even have to be the first one that gets there. So that's important. Now, master is non-blocking by default. Everyone skips it, everyone else skips it and keeps going. The barrier, so this doesn't have braces, it's just a line. You say big block, big fat block right here. And everyone stops and waits for everyone else to get there. Okay, there's nothing before it, nothing after it. That's all it does. It's just a big stop. And you should generally avoid barriers as much as possible. All right, and then a critical region is blocking by default. So we have if we set up a critical region and we do some stuff in here, okay, it's blocking in the fact that everyone stops at the top and then they all run through it one at a time. However, it's not blocking at the end, so once someone goes through, he keeps going. Does that make sense? And it's important to understand these behaviors in order to avoid what they call implicit synchronization or serialization of the code. Because these things slow your code down. If everyone has to stop and wait, that adds time to your serial portion of your code.
Question.
Yes.
For the critical, can you specify what order the processes go through?
No.
How do they go through then?
Whoever gets there first.
Okay.
And if someone is inside the critical region, then everyone else stops and waits for their turn.
Basically like a waiting line.
Yeah. Critical regions are used when you have a shared variable that needs to be updated. For instance, if you manually had to do a reduction for whatever reason, maybe you need to reduce an entire array, which you can't do in C++. You can do that in Fortran, but not in C++. So if you needed to manually update an array, a shared array, then you'd have a for loop in here, and you'd take the private numbers and you'd sum them up into the global one. But you can't do that all at the same time, otherwise you get data races and garbage comes out. So you have to do it one at a time. So that's where a critical region would be useful. There is, I think, let me see here. I love Stack Overflow, by the way. Okay, so ordered only applies to loops. It's not what I thought it was. You could manually set one up if you really wanted to. But I think that's about all you can do. I may be wrong. There's a lot to the OpenMP standard. But they do try and keep it as simple as possible. Okay. So now we need to talk about this ccNUMA. I will say I don't understand this very well. I only read about it today. But it makes a huge difference to understand at least as much as I've understood. So there's when you're looking at a multi-core processor. Want my pen? We're looking at a multi-core processor here, and he's got some memory over here, and all the cores can see all the memory. Okay. How this is actually implemented in hardware is rather important to us. So, for instance, your desktop computer is usually of the UMA variety, where everyone is basically can see everything. There's one maybe 2 memory channels. So it all kind of goes through the same highway. This guy needs a variable. He goes through that highway to get there, and it's all good. It also refers to the cache coherence mechanisms in the hardware, because if this guy has the number 1 for a variable, but this guy modifies it to number 2 and then flushes that out to memory, the cache coherence protocol then has to take that number and update this guy's cache here to a 2, which adds more memory traffic. So that's kind of your standard desktop computer, apparently. However, in a cluster design, typically we have what they call a ccNUMA architecture. And that stands for cache coherence something or other.
NUMA.
NUMA, hence the NUMA guy at the beginning.
Coherence NUMA.
I don't really know why it's called, what it stands for. It's in the book here somewhere. I read it. But it turns out the King's Peak nodes are of this variety. And so the way it works is we have our, sorry, I'm switching colors on you, our multi-core processor, and we have our memory. However, the memory is not all in one chunk. It's actually physically distributed. They can all see it, but let's say processor number 1, 2, 3, and 4. The memory itself is actually physically broken up into locality domains. And so processor 1 is directly connected here, whereas processor 2 is directly connected here. They have a direct link to that memory. And then there's a, we'll call it a switch for lack of a better term here. There's a big switch here, and this guy, the switch is connected to all 4, like this. And so if processor number 1 wants a value that's located in number 2, it has to go through the slower switch to get that memory. To us, the programmer, we don't notice that until we try and start doing high-performance computing. We don't have to care about that because the hardware is supposed to be taking care of it. But it turns out in this case, if we want to make things go fast, we actually do need to understand this. So any questions on that? How that works?
This might be a dumb question, but why not? Why does it have to have a switch when it's pulling data and not carrying data?
When it's pulling data and not...
Instead of storing it. Because it's storing it, it just goes... Or is it always using that switch when it's storing or pulling?
Right, because the variable that processor 1 wants is in number 2's locality domain.
Oh, right.
And there's no direct connection to it. And they do this for various reasons, I'm sure, but like I said, I don't completely understand everything about this. I only learned about it today. So each processor has a direct connection to its own locality domain and an indirect connection to the rest. And bad placement of the data in memory has a huge effect on the scalability. So let's say, let's just, oh, that's the wrong button. Erase. Okay. Let's just assume for a second. There's our processors. Here's our memory. Let's say all of your data is located here. Okay? And this just happens to be the locality domain of processor number 1. Processor number 1, he has a direct connection to it. So that's not bad. Whereas everyone else has to go through the indirect methods. The problem is they are all pulling, they're basically using up the bandwidth of this indirect connection. If they are, all three of these are trying to fight over this bandwidth here, then it really ruins your scalability. All right, so the question is, how do we take our memory and distribute it well in between the locality domains of 1, 2, and 3, and 4? Apparently, most ccNUMA architectures use a first touch policy for placement of memory pages. Memory is, well, okay, so we have the bit, the byte, and we can do kilobytes and megabytes and gigabytes, but we also have, apparently, what are called pages. And a page depends on the architecture that you're using, but a page is typically 4 kilobytes. Typically 4 kilobytes. And so the first touch policy is whoever writes to a memory page first gets the memory stored in their locality domain. All right, so that doesn't count for memory allocation. So in order to do this in order to evenly distribute the memory among the processors, we have to do this kind of a loop here. So we say pragma, OpenMP, parallel 4, and then we're looping through my array here, and we're just setting that equal to 0. So the memory is allocated here, and then we loop through this in the same manner as we would as if we were actually computing using it. Okay? Because then what happens is, if you do it in the same way, then each processor will always be operating on its chunk of the memory. Does that make sense? Seeing quizzical looks.
So what you're saying is, if we write this initialization as if we were computing, then each processor would, I guess, between the initialization and the computation, they'll be doing the same, or working on the same chunks.
Exactly. Because now, by doing this, let's say processor 1, he takes, j equals 0 to j equals 10. Okay, then those memory values will be stored here. Processor 2 takes 11 to 20, and those will be stored here. Processor 3 takes 21 to 30, and those will be stored here. And so then when you actually compute on it, processor 1, well, he always operates on j from 0 to 10, which he happens to have a direct connection to those. And so now the processors are not fighting each other anymore, because they all have direct connections to the memory that they are in charge of.
And that's specified by what? I mean, sorry, do you understand that?
It's like the first touch policy, right? So since each processor is working on that chunk to initialize it, rather than one processor initializing the whole thing.
Oh.
Right. If we did it the naive way, where we just, we allocate the memory and we say the whole array equals 0, then if we said the whole array equals 0, well, then the whole array would be stored in the master thread's locality domain.
So basically, by doing it like this, each processor is calling dibs on a chunk of memory.
Exactly. That's a good way to put it.
So,
Each processor is calling dibs on a chunk of memory.
so basically, all you're doing is just initializing it in parallel.
Yes, we are initializing
That's
it in parallel.
all you need to do, and it works
and it usually works itself out.
Okay.
The book does go into more advanced topics in Appendix A on how to do that, but they say that this actually works really well for most situations. As long as you keep in mind how you are doing the computation and initialize in the same manner.
Can I ask a favor of you?
Yes.
So we've talked about a lot of different memory things,
Okay.
and maybe I'm the only one, but it's hard for me to keep them straight in my head. We've talked about registers, we've talked about stacks, we've talked about caches, now we've talked about pages, and they all kind of seem the same to me. I mean,
Okay.
I know they're not, but
You want a handout on memory.
that would
Okay.
be really nice if we could have just like a quick reference of.
I can put something together for you. I can do that.
That would be great.
Alrighty. But anyway, now I want to give you a brief demonstration of how this impacts what we do. All right, so I just ran, I made these changes to my code. Oops, that's wrong. And I want to show you now, if everyone remembers from the last lecture, my scalability plot here got up to 4, and 4 was okay, and 5 then was kind of like a straight line over, and then it kind of just bounced up and down from there. Okay? But by implementing this first touch policy, now I have pretty much a perfect line, perfect scaling line, which levels off somewhere around a speed up of, we'll say 7.5. And if you remember from the scalability, for strong scaling, I can use that to estimate 1 divided by 7.5. My serial fraction for this code is 13%. Because that's where it's leveling off at. Whereas before, it was almost impossible to figure out what the serial fraction was because of the contention in the hardware for the memory. So make sure when you are actually writing your code to put this in there, to initialize everything in the correct way so you can get your good scaling. Alrighty. Any questions on that? Okay. Now we're going to talk about a little bit about MatPlotLib. Now this is what I use for plotting stuff, and it's very, I love it. It is a little dense at times, especially if you want to do complicated things. But if you want to do easy things, it's really, really easy. So on Linux, if you have Python, all you need to do is apt-get install python matplotlib python numpy. On Windows, there is an easy way and a hard way. Okay, I gave you a link to the easy way. And on a Mac, I'm pretty sure you can just use the downloader tool thingy that they have too. All right, so there's two packages, Python packages that you need to know. First is NumPy, or NumPy. It stands for Numerical Python, and this is Python's answer to scientific computing. Some people like it so much that they actually do all of their research in Python. It's written entirely in C or Fortran, which allows NumPy operations to be super fast relative to Python itself. because Python is a scripting language, so it is slower. There's a lot that goes on behind the scenes. If you want to use NumPy, you want to put this at the top of your Python script. Import NumPy as NP. So NumPy is a module in Python, and so we're importing this module, and then we are renaming it to NP for brevity. And then in order to get your data from a file that you've written, you use this function. This function is huge and has a lot of options, but if you write out your files correctly, it's really easy to use, and I'll show you that here. So this is my scaling. So this is what my scaling data looks like. So I have the number of processors here, and then the time it took to run the code. Okay, so that's pretty simple, straightforward. And then if we look at my actual Python script here, so I import NumPy as NP, and here I use numpy.gen from text. And what this spits out is a NumPy array, and in this case it's a 2D array. And then I can say the number of processors is going to be that first column that I had there, and this is how you specify that. The colon indexes the entire thing. It works just like MATLAB, pretty much, of column 0, basically. And then the times is column 1. And from here, I can compute the actual scaling parameters. So W, that's just the amount of work that we have to do. P is the performance. So we take the work and we divide it by T. And this spits out an entirely new array. So it does array operations, which is nice, or element coefficient-wise operations. And then we take that performance and we divide it by the serial performance in order to get the speed up. So this does, again, the entire array and divides it by the first element of the array. So that's your basic introduction to NumPy. Array indexing, again, is done with the bracket, the square brackets, and it does any dimension. You can have a 12-dimension array, and you just separate each dimension with the commas. Slicing is done with the colon operator. So if you wanted to slice from 1 to the end, you can do a -1. And so that skips the first element. I should say it's 0-based as well. So this is a slice of the entire thing. It's the exact same thing as if I did just a colon by itself. I could say I want values from 1 to 10 and skip every 2. Okay. Important thing to note, it is row major for multi-dimensional arrays. And then, so MatPlotLib. Let me go back to my demonstration here. So MatPlotLib, again, is a module. PyPlot is a submodule. So we're saying from the module MatPlotLib, import the submodule PyPlot, and then we get to rename it to something a little easier to type. And this is fairly typical. You see this all over the internet, these two lines here, when we're dealing with MatPlotLib. So if we want to plot a line, we give it X, we give it Y. We can then give it a format. So we can say we want a dashed line that is red. And we can give it a label, and the labels are used in the legend here. And so we just say plot this line. We can give it a title. We can label the x-axis. We can label the y-axis. We give it a legend, and then we use plt.show to actually display the plot that we're looking at. And there is another one called savefig, and we give it a name. And it will save it as that.
Like typing in the extension, the file extension will just
It figures it out. Although savefig has like dozens of options that you can give it to customize things. However, you're just going for cheap and dirty, that works. Python tries very hard to be cheap and dirty. I've found. So, but here's something else. If you do just plt-show, hopefully I didn't screw anything up. All right. So here, we can click this button, and it actually lets us start changing margin sizes and all sorts of things. I usually never touch this, but you can if you want to. Oh, you'll see we now have a dashed red line for our format there. This button, save the figure. And you can put it wherever the heck you want. It gives you a nice little GUI. You can change the type.
Didn't you already tell it to save though?
I took it out. I took it out. I would recommend either saving things as an EPS file, a PDF file, or an SVG file, because these are vector formats and they look really nice in PDF documents. Never save it as a JPEG. You can save it as anything else, just not a JPEG, okay?
Aren't PNGs vector graphics or no?
No, they're raster graphics. They're compressed. They're meant for internet. They were designed for the internet. Bitmap is about the simplest you're ever going to get. It's just a bunch of pixels. There's no compression. And they're really big. Yeah, they tend to be really big. So JPEG is a lossy compression, uses a lossy compression, which smears all your lines out, and I can tell if you used a JPEG, okay? JPEGs were meant for full photographs, and they don't work when we have a blanket of white with one red line, because then we end up with a smudged red line. Okay, so anyway, that. Then there's this one. If you want to do a contour plot, let me show you my example of that. Do I have? I do. We can do a contour plot. Very, yes. So again, this is my answer to the heat equation. And I have this Python script here. Again, we have the first two lines. And here we're importing the data. And the data is just rows and columns separated by spaces, so I can use all the defaults for gen from text. And we just feed that into a contour F. There is a contour. Which gives us just that. But that's really boring.
Is there a way to specify how many colors to use?
Yes. Contour F, again, takes dozens of options that you can use to
Probably just one of the input arguments.
change. Yeah, it is. And I forget exactly. We may even be able to specify it here. Just like that. I forget. Yeah, there you go. I think the default is 10 or something like that. You can,
That data.dat.
yes. I know, don't you love my naming schemes? Data.dat.
Plot.py.
Okay.
This is what it looks like. It's just rows and columns.
So you don't specify X or Y coordinates at all. It's just
Now,
You do
that is important. You do need to do that if you want a physically meaningful contour plot.
right.
And
For our purposes, it's basically
yeah, it's kind of a moot point, but and it's a little hard to do because you have to specify the X locations at every single point in the entire square. You can't. You may be able to feed it a vector of X's and a vector of Y's. I forget. I haven't had to make a nice contour plot in a long time, so.
'cause I know with the MATLAB version, you can put in vectors or arrays of coordinates.
Okay. Yeah, so you'll notice since I have 100 points in this, it goes from 0 to 100. Whereas if I'd given it X and Y, it would be from, 0 to 1. And then you can change the color schemes and all sorts of things. And then there's the color bar, which shows up on the right of that plot. Now, I will say this. PyPlot is supposed to be the nice, user-friendly interface to MatPlotLib. Okay? If you want to start doing really advanced things, really get down to the nitty-gritty, you have to throw out PyPlot altogether. And that's when it gets really hard. But for quick and dirty stuff, and you can actually make it look pretty nice just using PyPlot. So anyway, that's your basic introduction to that. It is extremely well documented. Stack Overflow has thousands of questions from people on how to use it, and I've found it extremely helpful. So anyway, that is my lesson for today. Again, tomorrow is just going to be a work day. No one shows up. I won't show up either. But if you do show up, I'll be willing to give you a hand. If you want to chat with me, then please email me and let me know. And I have an important contacts lens reminder. Anyway, so I will get the next project posted up today sometime. And your little memory thing. What?
Why post the next project?
What are you doing? Posting that on Wednesday.
I give it because I'm running out of things to talk about, and so
Already?
I'm okay with that.
anyway,
I think you should triple the number of projects.
triple the number of projects. Says the auditor.
The